We know now that in response to the arrival of an action potential, N-type calcium channels open. Then calcium ions enter the axon terminal. Calcium ions that enter a presynaptic terminal cause neurotransmitter release. What are the connections between calcium ions and neurotransmitter release? This diagram shows an axon terminal, which we call a presynaptic element, with the presynaptic membrane. This terminal contains synaptic vesicles, which contain the neurotransmitter. Here is the synaptic cleft, and across it, the postsynaptic membrane of the postsynaptic dendrite. Calcium channels are located very close to the vesicles docked to the presynaptic membrane. How are they docked to the presynaptic membrane? Now, if we zoom on the presynaptic element, only the presynaptic element, and here we see only here the presynaptic membrane and the vesicle with the membrane around it. There is a physical connection between each vesicle and the presynaptic membrane via proteins. For example, here, syntaxin, which is an integral protein of the presynaptic membrane. There are also connections between syntaxin and the proteins of the vesicles here that are called V-snare. There is also here an integral protein in the presynaptic membrane called T-snare. So V is for vesicle and T is for target. The entire complex here makes the vesicle attached to the presynaptic membrane and accounts for the fact that the calcium entrance is very close to the vesicle and very local. When calcium ions enter the intracellular medium of an axon terminal, they bind to a protein here called synaptotymine. It's a calcium sensor. What does it mean? There are sites where calcium binds, and when calcium binds, there is a change of conformation of the whole system, so that now the vesicle comes very close to the presynaptic membrane and the two membranes fuse. This phenomenon is known as exocytosis. The two membranes merge at a certain point and create a hole referred to as a fusion pore. The neurotransmitter molecules exit through the fusion pore. All these stages between vesicle docking and exocytosis involve a large number of proteins. These are complex phases which are not yet fully understood, and because they involve a change in protein conformations. And we are not going to explain them all. Afterwards, these vesicles are recycled through endocytosis, then refilled with neurotransmitter, which enables them to participate in another neurotransmitter release cycle. To summarize, an action potential arrives at an action terminal. It depolarizes the membrane up to around 20 millivolt, causes the opening of high-threshold voltage-dependent calcium channels. Calcium ions enter and trigger exocytosis and the release of neurotransmitter. It should be noted that even when all the conditions are there, for example, there are several action potentials arriving at the axon terminals, neurotransmitter release does not always occur. This is a relatively inefficient process, and only one action potential out of 2 to 20 will trigger exocytosis. How does neurotransmitter release stop once calcium ions are inside? How vesicle fusion and exocytosis stop? This is due to multiple processes that allow the presynaptic terminal to return to a quiescent state. There are inactivation of sodium, as we saw, sodium channels of the action potential, but also of calcium channels. We have seen that these channels inactivate. So this stops calcium entry. To repolarize the membrane, we have voltage-sensitive potassium channels of the sodium action potential, and it allows the repolarization of the membrane after the action potential. And we have also in the membrane of the presynaptic terminal calcium-sensitive potassium channels. It means that these channels are opened by calcium ions. When the intracellular concentration of calcium ions increase, it triggers the opening of these potassium channels. And we say that it repolarizes calcium action potential. We did not say that before, that we have an calcium action potential. It's because when calcium ions go in, they depolarize the membrane, and this can be called a calcium action potential. These potassium channels that are calcium sensitive are not explained here, they are explained in a supplement. But what about the calcium ions that are already inside? Where do they go? They are ejected from the cytoplasm via multiple processes. Pumps that use ATP energy to eject calcium channels, because I remind you that it is against the electrochemical force, so they go outside. You have transporters that exchange sodium with calcium, and you have here also a pump that put calcium ions in stocks, like in the reticulum endoplasmic. And you have calcium binding proteins that bind calcium, and like that, calcium is no more active because the active form is the ionic form. All these mechanisms are called the clearance mechanism for calcium ions. All this makes the increase in intracellular calcium transient, very brief, which means that neurotransmitter release is also brief. In summary, let's look at some quantitative data. The depolarizing phase of the action potential, of the sodium action potential, opens voltage-sensitive calcium channels present in the axon terminals. As a result, calcium enters the presynaptic terminal. This entry is very localized. Here you see 0.3 micrometer square. And this is transient because calcium channels inactivate and the membrane quickly repolarizes. When you have an increase of the intracellular calcium in the presynaptic terminal that reaches around 0.540 micromolar, then this triggers exocytosis because they bind to a sensitive protein and very quickly, in 200 microseconds, they induce exocytosis. This means that the entry of calcium ions and the binding to calcium-sensitive protein and the changement of conformation is very quick. The repolarization of the membrane terminal is due to potassium currents, either activated by the depolarization, like potassium currents of the action potential, that are called delayed potassium current, or the calcium-sensitive potassium currents. We now know that the action potential is created by ion currents, because sodium and potassium ions are passively transported across the membrane. This electrical signal, the action potential, created at the initial segment of the axon, and traveling along the axon arrives at axon terminals. At the axon terminals, it depolarizes the membrane of the axon terminals, opens calcium channels, and causes calcium ions to enter. This inward transport of calcium ions is detected by calcium sensor proteins and results in the exocytosis of synaptic vesicles containing a neurotransmitter. This way, the neurotransmitter is released into the synaptic cleft. In the following courses, we will see how the neurotransmitter recreates an electrical signal, which is called a postsynaptic potential.